Dear colleagues, friends, and partners, welcome to ATP's webinar session on how can NVMe SSDs beat the heat. My name is Chang. I am your moderator for today. For this webinar, we would like to dive in with you and take a close look at heatsinks and other thermal solutions for NVMe drives. Our speaker for today, Chang, is the Senior Manager of Product Management and Head of the Removable Storage Business Unit at ATP Electronics. During her 12-year tenure at ATP, she became the leader of the Automotive and Thermal Task Force and has successfully designed in many global projects in industrial and automotive applications. Without further ado, let's begin the presentation and welcome Chang.
Hi everyone, this is Chang. Thanks for joining the webinar. I hope today's presentation benefits you in some ways. Now let's go to the subject. What is SSD thermal management? For me, it's like running a marathon. Is it interesting? I can quickly list 5 things in common: environment, physical conditions, training programs, the gear you wear, pacing strategy, which link to our goal: steady wins the race. Let's start from understand the environment. What are the weather and road conditions? Just like what's the system's environment? It can be a box PC, data logger, IoT server, on the various temperature, airflow, and customers' criteria. Like running under the sun, people provide water and supplies. Some systems, they install powerful fans or cooling plates for heat dissipation at high temperature. Then we evaluate the physical conditions. We apply the Cadence simulation during product design phase for IR job, signal integrity analysis, and thermal simulation. By filling component package information, such as case dissipation, power loss, PCB dissipation, junction temperature, case or board temperature, etc., we're able to generate temperature distribution result. It's the distribution of heat in each PCB layer. Below images shows PCB top layer heat dissipation distribution as an example. And there will be the heat distribution of PCB layer by layer. And this result can help our hardware engineers consider the adjustment for our layout circuits, wire thickness, the quantity and the position of through holes, and so on. It is also important to consider the physical condition of host devices. When the system is developed, the mechanical design includes SSD, yet the need of heatsink may come later. Is there enough space inside the system for heatsink? We have to evaluate the surroundings, the top, bottom, and the width of the SSD. Is there any mechanical interference? The components on system PCB may overlap with the SSD heatsink. Let's assume there is the room and space, and we expect a good thermal dissipation. We can use the example of 8mm fin type heatsink. As you can see, the fin type have more surface space area for the heat dissipation. It's lightweight aluminum with good thermal conductivity, a good adhesiveness of thermal pad for the conductivity, and we are using the clip design for assembly efficiency. The clips is more reliable for top and bottom heatsink fixing, and it is so thin. Here, only 0.3 millimeter stainless steel to save room for systems with limited space. And then we put all the elements together. The thin type heatsink, thermal pad, SSD, stainless heatsink together becomes our NVMe M.2 2280 with thin type heatsink. After evaluating the environment and physical conditions, it's time to arrange the personal training program. The Cadence simulation software can run system-level, module-level simulation with customers' input for ambient temperature, airflow, and the parameters of ATP SSD drive. The thermal simulation shows the estimated temperature with or without heatsink solution. Here are two scenarios. The ambient condition 55 degrees Celsius at 600 LFM airflow. Another is 70 degrees Celsius, 1200 LFM. The simulation result is pure hardware under full operation mode. So you can see the control temperature, the simulation result is quite high. The controller area of bare SSD is around 156 at 55 degrees Celsius. Here. When we increase the ambient temperature to 70 degrees Celsius, with sufficient airflow, the control temperature is actually reduced. So that shows how important that airflow in this simulation result. Of course, with the 8 millimeter heatsink, the overall temperature is reduced. Well, you may have the questions why the temperature result is a little bit weird when we are under the different ambient temperature and different airflow. We will give you more examples in the following slide, but to remember, this is just the hardware simulation result. And we provide the solution is a combination of our hardware design and our sophisticated firmware algorithm. Apart from the simulation by software tool, we could also run a real SSD test in ATP-Built mini chamber. It is smaller, like notebook size, a little bit taller as well, and flexible compared to the standard giant chamber. When connecting to the PC and notebook via USB port, we are able to control the test environment, changing the airflow conditions, changing the ambient temperature. We also equip the alarm alert design for the emergency stop overheat protection. Furthermore, we can also access the smart temperature, select the different SSD workload, and save the log file. Now we have to find the suitable gear. Start from the material selection. There are too many factors to be evaluated. We list only a few examples. First of all, thermal conductivity. Silver and copper can have better thermal conductivity. However, aluminum is weight saving and less costly with good thermal conductivity as well, normally in the form of fin type design. Mechanical engineers evaluate the cutting and shape of fin surface and airflow field to enhance the heat exchange coefficient. We are also evaluating the reliability. The resistance test at high-low temperature on adhesive layer to assure there are no deformation. And the third one is the shore hardness scale. Soft pads attach closely between the heatsink and SSD component. Yet, if it's too soft, the percentage of silicon is high, and the heat dissipation substance is low, which could lead to the poor thermal conductivity. So it seems that there are a lot of pros and cons, and there are so many scales we have to evaluate how we do it efficiently. Well, you have seen this picture in the earlier slides. It's a thermography image that you can use as a simulation tool to find the best candidate. And this is the picture we took with the real test. It was taken at room temperature, minimum airflow, 100% sequential write after 30 minutes test. The controller temperature reduced around 30 degrees Celsius after equipped with the 8mm heatsink. So this is the bare SSD, and you can see the temperature gradually reduced when you equip with a more powerful and thicker heatsink. But not every system can have enough room for a powerful heatsink. So we do consider that and offer different solutions. It could be the copper foil, the thinner one, 4mm fin type heatsink, or the most powerful 8mm fin type heatsink design. Here is another example. When you select the right gear, you will be surprised. What you wear keeps you cooler. The marathon runners wear outfits made from quick-dry fabrics that absorb sweat fast and pull moisture away from skin. And it's just like the thermal management and the heat dissipation on the SSDs. When the composite temperature keeps increasing, let's see here, the SSD repeatedly slows down to cool it. But with the 8mm heatsink, dissipate heat complemented by airflow support, the maximum composite temperature of NVMe SSD is reduced here. And of course, the performance is steady with the optimized firmware algorithm. That tells us pacing strategy is just as much important as above factors to achieve the goal with good scores. Steady wins the race. We have to managing the heat while keeping performance optimized. Dynamic thermal throttling mechanism provides a delicate balance between performance and temperature by continuously detecting the device temperature and adjusting the pace. From system viewpoint, the benefit of pacing strategy are lower power consumption here. Here. You have the pacing strategy, steady speed, efficient power management. Of course, if you always run under the full speed, just waste a lot of energy. The benefits of pacing strategy are low power consumption, less fan operations, energy saving, and less noisy. So some of our distributors, customers, sales may familiar with this page. It's actually the summary of the simulation and customization tests we have done for our customers. And just a good example that one scenario doesn't fit all. There are 5 scenarios we put in the table, and with different environment, no airflow, 600, 100, 1200 LFM, different temperature, different workload. It may not be 100% sequential write. It could be the sequential read. And different system, mechanical design. Some of them need copper foil because there's just not enough space. And some of them we can equip with the thin type heatsink. And the test result also varies. I would like to highlight that it's not just only seeing the reduce of the composite temperature. We also value the temperature slope rate of bare SSD and with the heatsink. So I believe that it shows that we are able to do a lot of customization, and we would like to do more experiment with our customers. Welcome to discuss your scenarios and build optimized thermal solution with ATP. We offer M.2 to AT and U.2 NVMe SSDs. And let's win the race together. Thanks for ATP Thermal Task Force team members. And if you would like to know more, we're looking forward to hearing from you soon.
Thank you, Crystal and the Thermal Task Force team. We hope that we provided some insights to you today, and hopefully this leads to more questions that we can help you with. We will follow up this webinar with an email. Most importantly, you are welcome to reach out to us via this email with your questions and inquiries in a more in-depth manner. We'd like to thank everyone for joining us today. Stay safe and have a great day ahead.